Hello, everybody, and welcome. Oh, God. I didn't mean to actually click that. Hello, everybody, and welcome to Handmade Hero, show where we code a complete game live on stream. Yesterday, we did all the work of optimizing the grid stepping. And I did it in the actual table building code so that I could verify it against our table-driven version. And so that way, I have some reasonable confidence that it will just work. So today, what I would like to do is actually put it into the main code so that I can do the change, I can make the change that I actually wanted to make. And so part of the thing that I want to do here, if we take a look at what we've built so far, I have a nice way of verifying or I shouldn't say verifying, measuring the slowdown. So if I actually go into Handmade debug here, and I run hhlightprof, like so. One thing we can do that's nice is we can look at what our total time is right now in terms of the speed at which things are going. And we can sort of see that we're hovering around 4.5 seconds, and there's some variability in there, as you might expect, depending on what the OS is doing and so on and so forth. But we kind of know how long our routine takes to function right now. And so what I wanted to highlight there is just as I make this switch, I want to see if it costs me anything. So right now what we're doing is we load, you can see us sort of passing it in here. You can see us loading this walk table. And so the way that this works is every time we go through this loop and we do our array casting, we access the next, we basically look into that walk table to figure out what grid square we're going to, or I should say grid cube, we're going to access next. And so what I want to see is, can we now sub in just the raw code from the walk table routine and effectively get our walking inlined with no table lookups without actually paying any significant performance penalty? Again, if you're here yesterday, you know the reason why I want to do that. The reason is just because I want to be able to make the sizes of our grid squares significantly larger than the lighting voxel. That's just so we can do more iterations of the inner loop to test. And right now we're really underfilled. And again, if you missed yesterday's stream, that's what this is showing. We really want to slot into these much more cleanly. We want a lot more higher numbers in here, so we want box count, 16 and stuff like this. And furthermore, we really want to reduce the count here, and since this is just representing empty space, the only way to reduce that count is to reduce the size, right? And what you can understand there is we're traversing these grid squares as a way of reducing the number of things we raycast against, but when that number reduces too small, we just are wasting too much time iterating over the grid, right? And it's really easy for me to just change that size. It's just a few parameters we can just play with, right? But the thing that would hold us back is the walk table. So we just need to go make sure, right, that we can actually do the walk generically without a table. And so that's what I'm going to try to do now. So if we go down to our compute walk table fast routine, in here you can kind of see us doing the setup and so on. And we have a few tables that we need to use that are just local access tables. Those are cheap and pretty easy. So I should be able to just stick them in here. And furthermore, once we actually have these tables lined up in here, we will also be able to replace, if we want to. We could, I think, probably do an extended version of the best table. If we wanted to do an extended version of the best table, we could probably change from using the mini PU16 hack that I did here, that I feel like was kind of fancy and smart, but sometimes being fancy and smart just makes you fancy and dumb. So I'm not sure that this was really a good idea because of the accuracy concerns and so on. So I'm not really sure we want to leave that in there. So now that we've got a way to kind of do this, and we're already using a table to drive the T comparison, and we know we need that one to be accurate, We can probably extend this to this table to be 16 long. And if we, I mean, honestly, we can change this to a U8 as well. So if we extend this table, we could then use it for the other comparison probably, right? So just something to think about. It's in the back of my head whether I want to do it or not. I don't know, and it doesn't really matter right now, but it's just worth noting that we may be able to, more or less for free, because we already paid for the tables and they're already in the cache, we may be able to just replace this with a more accurate one, and that may be something we want to do. Right. Just something to think about. Okay. So if we go and now take a look at what's going on in the table building loop that we already optimized, you can see the stuff that's happening here is fairly straightforward. And then at each time we want to take a step, it's just this code at the top, right? It's this code here. So I believe if we just go down here and we take a look at when it's using the table, right? I should be able to do something where I can just validate this against the table directly in line, right? So what I could do is say, okay, I'm going to grab this code. Here's the code that actually does the walk, right? That's it right there. And all it's doing is it's just taking the t values, moving them forward by the amount they would go in each of the dimensions, seeing which one hits first. So do we hit the x wall, y wall, or z wall first? Updating the tracking of where we are, and outputting, basically thanks to the best table, outputting which one of the columns, was it x, was it y, was it z? So if you take a look at what we actually need to know here, we just need grid index and t-terminate, or more specifically, we just need dgrid and t-terminate. And so we kind of know at that point we can get those two out by just doing these two. We can extract a t-terminate if we need one, and we can extract a dgrid result if we need one just by looking at these. So the step table or t-terminate table. And so all I want to do here is, again, I want to do the exact same stuff I was doing. So I basically want to do this verification and basically have it just fault on me immediately if they don't verify. I want to do that verification against these values. So I don't want to update the walk table just yet, right? I want to kind of do that afterwards just so I can see, like so. But another way I could do that, and maybe I'll do it just for fun, is here I'll just do like what was the dgrid value. I'll just read it out. That way we're not reaccessing that table. So we've got the dgrid and the t-terminate there. And what I'm going to do here is just take and say I want the t-terminate and the dgrid values to line up, like you can see. And that way, as soon as there's a problem, it will crash, right? So I'll fault immediately upon there. And again, the reason for that is because sometimes we turn asserts off when we're building in release mode. And so I just want this to fault all the time right now. And then when I clean it out, we'll be done. So that should do it. And now what I need is the preamble, right? So you can see here, we've got some issues though, like the shuffle table. The shuffle table is a little bit different, right? And I have two of them. This one is, and one of the things we'll probably want to do is unify these shuffle tables, right? And we may be able to do that. But for now, I don't care. So I'm just going to call this like the T shuffle table. And that one can still be called shuffle table. So down here where we access it, there's really only one place, right? All it does is do that one shuffle to get everything into the right location. So it's pretty straightforward. And then what we need is, you can see all of these 4 values are not actually, they don't exist, right? Because we set them up, excuse me, we set them up here. So what we want to do is we want to bring those values into the system, and it's a little bit tricky because the way we chose to do this as x, y, the way we chose to do this as x, y, x, z, again, that causes some problems for us. So it makes it not line up very well with the other things we have. To be completely honest with you, I think the reason we did it was probably not a fantastic reason. So the reason we did it was so that we could actually just make this table be shorter. But that looks pretty dumb now, doesn't it? Because if you look at what's going to happen when we integrate this routine, all of a sudden we're going to need completely different values for each of these, right? Which is a huge pain in the butt. So actually, maybe we don't want to do that yet. Like, maybe that's actually dumb. And maybe what we actually want is to go back to that routine and just make it work with XYZX, right? I don't know. It's unclear to me. Like, I want to double check that makes sense, but I just think it would, because if you take a look at what happens here with like ready packed and stuff, we already kind of have what we need, but we just would have to add like the X in here, right? And even if we didn't want to do that, we could even just leave that lane as 0 if we wanted to. And if we did that, we still would probably just be able to make this work. We just need one extra shuffle, right? We just need to replicate the X before we do anything. So it seems kind of motivating to do that. So if we take a look at ready-packed and where that actually gets used, you can see it getting used in a bunch of places for initialization as well. My only question is, like, what are we doing with that one lane there, with that lane being 0? Like, does that always get knocked out or doesn't it, right? And that's pretty tricky because I don't know, like, we've optimized this code quite a bit, and so we're kind of past the point of this being versatile code. Like, we're in the speed zone now, so everything's like very concentrated. And so it's hard for me to know, like, to what extent we may have relied on that for tricks, because it's hard to, you can't really document every little thing you do when you try to optimize a piece of code, and so it's, it's kind of difficult to say. But we can kind of take a quick look and just see, like, do we think we could just stack an X in there? And again, another thing we probably want to do is eventually just test these routines a little bit hard, because we can make constructive tests where we make specific shapes and stuff and make sure we hit in the way we expect and things like that, right? So, like, looking, just looking at this stuff, though, I honestly don't know that there's a huge issue there. It doesn't look like it, right? Because most of the time you see it's extracting out, and it just doesn't really look like it particularly cares, because like things just get knocked out all the time here. So it doesn't really look like the kind of thing where it's going to care if we used that extra lane. So I think I'm just going to go ahead and say, like, either way, I want to go to that fast routine here, and I just want to do a little bit more work on that. So let's just make sure. So if I go and launch this in the debugger, I should be able to make sure that we're still validating correctly. So if I run it, it works. If I go in here and I change this table to be like incorrect or something, like let's say these are 2s now, it should just fault immediately as not matching the results that we expect, right? And again, this is just for me to make sure that our safety net is still in place while we make these changes. So when I go down here and I want to do this reorganization, so if I just move the X's to the end, for starters, that looks like this. Oops. So now we're packed XYZX, XYZX, XYZX. And when we come down through and we do any of our extractions and shuffles, these might be slightly different now, right? So the first thing we'll see is when we do this shuffle 4x and we're trying to line things up, what you can see is we're doing 1, 3, that's for the x, y. Those are the same, so that's fine. And then when we do the T4, we're doing z, z, and yeah, it doesn't really make a lot of sense. So, you know, now that I'm kind of looking at this, I'm also wondering to myself, did we even really need that in the first place? So, like, we could have just shuffled the x into here and done the x-z comparison the wrong way around. So I don't actually even know if we need this padding. So maybe what I would say there is let's do this one change, then I'll try the actual act of also just leaving this lane 0 and switching the order of the comparison, because it looks like we could get away with that too, right? So, all right, so if we change that comparison order, here is our mask table. And the mask table, you can see every time there's an X, it has this channel in it as well. We would want to change that. So now what we would be doing is we'd say, look, when we are doing X masking, we're only talking about the first lane. Similarly, when we're doing Z masking now, we would be talking specifically about the third lane. So, you know, it would look like that. So Z is third lane, Y is first, well, 0th lane is X, 1th lane is Y, and second lane is Z. Right. So the last thing we have to update is the best table. And the reason we have to update the best table is because now the best table would actually be 16 wide. And so the X less than Y would be the same, the Y less than Z would be the same, and the X less than Z is now not in this channel. So it's actually like there's a phantom channel here, right? And sort of what we're saying is we don't care what this channel is, right? Like we don't want to care. And so, and this is an interim step. Like I said, we don't really want to actually do this, right? But, you know, that's just where we're at. So if we continue the bit pattern here, you know, that's what we would get here. And it's going to be the same in this case. And then we would do, you know, a duplicate here as well, right? So you'd just say like, oh, okay, it's going to be the same. And again, I don't think we actually want to do this, right? But I'm just trying to do it one step at a time so that we can validate sort of things in the interim, because it's fairly complicated code, right? I don't really want to have to do it blind. So again, same thing. So now when we look at like the shuffle table, so the shuffle table in this case is doing the same lookup that you would be doing here. And again, you know, it's going to be a little cumbersome at first, but that's fine. So it is 0, 1, 0, and then the difference here is 2. Is not this. Like that's picking the final lane, but we actually want to pick the middle lane. So this is an 8, 9, 10, 11. Like so. And so that's the 0 and 0, 2. We would duplicate that much like we duplicated it up here, just because that middle bit we don't want to care. We're just not going to look at it ever. So we're just going to leave it out. And then we get to the second part, which is 2, 1, 2, 2. And again, same problem. These 12s is not what we actually want. So we just want to replace those like so. And then we're just duplicating that twice. And so you can see this like expands our tables quite extensively. And that's why I think we want to just stick with doing the 3 wide version, because it just keeps everything smaller. But I just want to do this one first. All right, so now let's debug it. As you would expect, like it's probably going to be busted. The mask table is wrong, though. No, I just realized that. we didn't finish this. There we go. All right, let's try that one more time. And I probably want to go into debug mode for this as well. I might just let these be auto. Yeah. I want to go to debug mode because I want to be able to go through it and see what's wrong and so on. So I want to kind of just do a quick, yeah, there we go. All right. So now what I want to do is I want to kind of see like what's going wrong here. You can see that I think the tables are roughly correct. If it's 0, 1, 0, 2, 0, 1, 0, 2, right? It's 0, 1, 0, 2, 0, 1, 0, 2, 2, 1, 2, 2, 2, 1, 2, 2, 2, 1, 2, 2. The mass table is 0, 1, 0, 2, so 0, 1, 0, 2, 0, 1, 0, 2, and 2, 1, 2, 2, 2. Wait, that's wrong. Where'd it go? All right, so, well, I was thinking I had it right. I don't. Yeah, bit twiddling. It's always very finicky. All right, let's try that one more time. So 2, 1, 2, 2, 2, 1, 2, 2 down at the bottom, right? And so now I can take a look at what we're actually getting here in the registers and see what's going wrong. So let's take a look at what all these actually are first. So looking at the values, we know when we're doing T4 and T4S, essentially T4 is X, Y, and Z. And, oh, well, and that's wrong too. So we have not finished updating this routine. This we moved from lane 3 to lane 2, so that's supposed to be 2. Lane 3 just has X in it, and we don't actually want X anywhere on the bottom. That was not a thing we're actually doing, so I don't know what that was there for. Again, we might change that eventually, but again, wasn't quite right. Okay, so let's try that one more time. So let's take a look at what T4 equals, because T4 in this case, like we always want everything to be X, Y, Z, X, and you can see we initialize it that way, X, Y, Z, X, X, Y, Z, X, always at the top, right? So now if we take a look at what these actually equal, I can start to just validate whether or not any of this stuff went correctly, right? So our T4 and our T4S, they never get modified, so I can watch exactly what happened to them. And you can see here, so we've got our T4, here's our X, Y, and Z stepping values. So that's like, you can see here that we're supposed to be picking like the Z step, because it's the lowest. I'm gonna get some extra T here. All right. Okay, so what I was trying to say there is, if you look here, these are the T values we computed, and now you can see that we've got this Z value here. And so here we're trying to rearrange these so that we have Y, Z, and then just Z, right? And that's what we have, Y, Z, and Z. So that shuffle appears to work properly. We have a min comp here, which will show us if we look at what the comparison is. So here's the min comp. You can see here that this is trying to say like what's greater, right? So in this case, 9 is not greater than 27. 1 is not greater than, 27 is greater than 1. 1 is not greater than 1.4 or whatever. And so this is the only channel that we get as, you know, a positive, right? So then we say, okay, let's move the comp mask out. So that's going to basically take, and it's going to look at the high bits of each of these. So what we would expect to see here is 0, 1, 0, 0 from the LSB out. So that's just going to be 2, right? here, which is what we get. And then we're looking up into the best table here to see what the best dimension is. So let's make sure our best dim is correct, because maybe this is wrong. So yeah, if we look at what we actually have here, that's just wrong. So let me look at what's going on in that. So what we basically saw, right, is we saw just this one bit set, right? And so we basically said if x greater than y is less than z, wait a second. Bring me back there. Bring me back there. So we basically got our comparisons. We said x and, we're doing a greater than. So in this case, x greater than y is what that's doing. And x is not greater than y, right? So that would mean that x is lower than y. So we want to then know if x is greater than z, right? And so x greater than z should also be false, right? Yeah, so we should have been keeping x because x is greater than z. Am I wrong about that? So we should be keeping x because x... And that goes the wrong way around, too. So we changed these partway through. These should be this way, right? Because, I mean, that's what we're looking at. We're looking at it this way. Am I wrong about this? Not sure why we wrote it that way. Because that's what the comparison is. It's blank greater than blank, right? So in this case, we're looking to see, did x compare greater than y? So in this case, x did not compare greater than y, so we keep x, right? Y and z, we don't really care about what that actually is. So in this case, well, I guess we're up here. In this case, it was here, but we don't care about that. So all we now need to know is x greater than z, right? And the weird part here is it looks like we never did that somehow. Like, the T4 value here, like, that's supposed to be x. Right? X, x, x. So how is that value... Why is that value 0? That's why. So this table here, if we want to keep something in that lane, we need that mask to work. All right, that's fair. So basically, we forgot to replicate the x out here. Right? I removed it from this column, but I forgot to add it in this column. Looks okay. All right. And now we're good. Okay. So that works just fine, but like I said, I think it's a little bit unnecessary. And so what I'd like to do is make one more change, which is just to not use that fourth lane because it just creates larger tables for no real reason. And there's two ways we can do that. One is we can put the shuffle in here, and the other is we can be a little bit more clever about the way we do the comparison so that we actually just do the XZ comparison the other way around. Now, normally you'd start there, but because we're comparing against a routine that doesn't do this, that means we may have a switch there. So I'm going to do the shuffle first, and then we'll switch. Although I don't actually know that that helps. I think about it. You know, it really doesn't. So maybe we ignore that. But anyway, so if you take a look at what's going on here, right? What I'm saying is we don't care what this value is particularly much, right? It just doesn't matter. So what we can do there is say, look, just leave that as 0. So we know that this will always just be zeros in that final column because everything in it will be zeros. So just leave it as 0 so that we never get a true comparison. It's always a 0. And then what we do here is say, look, put x in there so that we just do the x comparison the other way around. So at that point, then you could say, well, now we don't need to worry about lane 4. Or lane 3, I guess. I don't, depending on how you want to say that. We don't need to worry about that lane. We're just going to leave that lane out of it. And then we can just get rid of any of this stuff, right? So we don't then care about that final lane, like so. And then all our tables can shrink again. So at that point, we can then say, all right, we don't need this extra duplicative version here. We can just shrink it back down to 8. And the same thing would go for basically all of our tables. So we don't need that, and we don't need this. So now it's much more condensed. And up here, we can do the same thing too, where we say, all right, we only need these. But we also now need to kind of reverse the idea of what's happening here. So if I delete this part, that's all well and good. But we now have a different meaning for our final column. So we don't, like, this is not this anymore. It's actually that, right? So in every place that previously we were picking an x, we would need to pick the z value. And in each case where we were picking the z value, we'd need to pick the x value because we flipped the meaning, right? So if we take a look at what happens here, all of these, right, are like, is x greater than y? It's not, so we take x. Is y greater than z? We don't care. Then is z greater than x? And if it's not, right, then we would take z. But it is, so we keep the x, right? Same thing here. In this case, if x is greater than y, then we keep y, and if y is not greater than z, then we continue to keep y, right? And so we don't really care about that. In this case, where we've got the 0 here, again, x is greater than y, it's not, so we keep x. We don't care about this value, and then we go here and say z is greater than y, it is, right? And then finally, this last one here, where we're like, x is greater than y, is true, so we would actually keep y. Y is greater than z, so now we keep z. Z is greater than x is not possible at that point, right? So really, we don't care what this value is at that point, because that creates like you can't really have that comparison. You know what I'm saying? So then if we come up here and we say, let's see what these do. So this is x is greater than y, so it's not, so we keep x. We then say z is greater than x. It's not, so we keep z, right? X is greater than y, it is, so we keep y. Y is greater than z, it's not, so we keep y. X is greater than z, it's not, so we keep x. Z is greater than x, it's not, so we keep z. X is greater than y, it is, so we keep y. Y is greater than z, it is, so we keep z. And again, these are not possible, I don't think, right? So in theory, we should be able to use that because, you know, although there's the equals case will come out differently, we don't care which one we use in the equals case, right? So we may not be able to validate this against the old routine, but I can rewrite the old routine slightly to be the same. So we should be able to make it work if I'm not missing a case, right? But I don't know, so we'll see. Okay, so this is a problem as well. So actually we need to take care of that. So hold on one second. So we need to figure out, okay, so one of the problems is like invdarray for there. So the inverted version we use here, I kind of need that to make sure that that's just going to be 0 all the time. So I may do that a slightly different way, because I want that to just be easy for me to read. I don't want to be seeing crazy stuff there. I want that to be 0 just so I can, for my own, just for simplicity, for my own sake, right? All right, so let's get started looking at this. So if we take a look at what the comp mask is here, we're in the exact same state that we were before. I don't actually... Wait. So something's weird about that, possibly because of the way I was masking it or something. So t values should never be negative. So I screwed something up there that we need to address. Which is what? Oh, it's very simple. The mask table is different now. So it's 21220102, right? So 222, so there's 2122 and 0102. So 0102. All right. I was gonna say that's just nonsense that we're seeing there. So let's try that again. Still bad. Did I mess it up twice? Unsurprising. These things are very finicky, so. So I may not have messed this up, but I may have messed up the construction of this table, right? So this one here. So I think this aligns right, because 2122, 2122, 0102, 0102. So the mask table and the best table look correct to me. Oh, but the shuffle table, we didn't do that one yet, did we? So in that case, that's 222, right? And there's the 1. So 2122. And then here we have 0102. So 0102. I don't know that that would have done it, though, so I don't think we're out of the woods yet on that. I think we've still got an issue here. Okay. That's a new one. So I'm going to step through this and see where that comes from. But I think these are all in line now, right? 2122, 0102. So 2122, 0102. Yeah. Okay. Good deal. So now I just want to see what's, what we're actually doing here. Let's step through this one at a time. Just want to see what's happening. Okay. So there's our T computations. Probably, yeah, well. So we're supposed to pick the second thing in the comp mask, which comes out to be 2. So that's suggesting that Z is the best value. That's correct. So that part worked fine. So let's take a look at what we actually select. So that did correctly select Z, so that's good. And so our @4 now just gets advanced by that much. Like we can look at that as well. And then what we want to do is we want to take the, because we went one cell forward in that direction, we want to subtract out that dimension, which would be 1.4. So this should now get zeroed, and it does. So that whole thing looked good. So I guess what I would say is we probably have a bug in one particular part of the table. So, because it's all working right now. That all looked exactly correct. So unless I just spaced, that's right. And so what I probably did is when I was reading this off, I probably just made it a mistake, right? And I can check it one more time just to see if we can catch it by inspection. But otherwise, what I'll do is I'll step through till I see it, right? And then we'll just fix it there. So in this case, one way I could write this is x greater than y. So this is y less than x is this case. Oops. Right? So y is less than x. Y is less than z. I'm sorry. X is less than y. Y is less than z, right? And x is less than z. No, sorry, z is less than x. Right? I mean, I'm just, you have to flip these. So these are 0, 0, 0. So they're going to flip each time, right? So I guess I could do it this way. This is z less than x. Y less than z. X less than y. Right? Because every time this is a 0, it flips. So if we take a look at that, if z is less than x and y is less than z and x is less than y, is that one of those? That's like, I mean, that's that triple, right? So z can't be less than x. Like, that's one of those ones that just doesn't work. Like, one of those two things has to be wrong. You know what I'm saying? So I wonder if you can ever actually get that case. Like, shouldn't that case not really be the thing? I mean, I guess you could say, well, it's less than or equal to, right? Because it's not, it's actually that, right? So in that case, it could be that they're just all equal. Would be, I guess, one way that could be true. So I think that's what that means. So we could literally pick like anything. You know what I mean? Like, no matter what we pick, it's right. So let's take a look at this one. So this one is x greater than y, y less than or equal to z, z less than or equal to x, right? So in that case, I guess we would say if x is greater than y, then we know that x is kind of out of the question. So we're really just looking at these. So if y is less than or equal to z and z is less than or equal to x, we're really just talking about that. And so that looks right. That's y. That's right. So that's fine. Here we're talking about x less than or equal to y, y greater than z, z less than or equal to x, right? So here we would say if x is looking to the y and z, so that's this, right? So that's clearly z. Here we would say x greater than y, y greater than z, and that's just this, right? So that would also be z, pretty clearly. I mean, z greater than x is false, so that means it's that, which is not possible, I want to say. Because how could x be greater than y, which is greater than z, but then suddenly z is less than or equal to x. Like even equivalence doesn't do that. In this case, I believe because they could all be equal, like this one you could pick any. This one should never occur. We should probably assert that. Okay. Here we have s less than or equal to y, y less than or equal to z, and z greater than x, right? So again, if we junction these, we just get that. And this says that z is greater than x, which is what you would expect. So that just seems like x, and that's fine. Here we have x greater than y, y less than or equal to z, z greater than x, right? So in that case, I believe you can just junction these two and just say, well, it's y at that point. Y less than or equal to z is also correct. So that just seems like y, and that's exactly what we put. In this case, we have x less than or equal to y, y greater than z, z greater than x. So that's this again. X less than or equal to y is exactly what we would expect. So again, that should just be x, and it is. And then the last one is everything's true. So x is greater than y is greater than z, z is greater than x. Right? That's not possible. I want to say. Oh, wait, no, that's the wrong. Okay, no, that's actually fine. Z less than or equal to x is allowed here. So that's fine. It's this one that is not allowed because z can't be greater. So it's just this one, I think. Does that seem right? So I think that one is actually bogus. Oops. Ah, what's happening? Stop. No. Bad. Okay. So I think this table is correct. I don't know. It seems right to me. I don't see where that goes wrong. It's possible that when you hit this one case, so this case here feels like it would differ from the. So, you know what I could do though? In the case where they're all equal, I do know what the other routine would pick. So in the case where they're all equal, this routine would pick x. So I should be able to say that. Right? All right. So let's see, like, how long does it take this thing to fail? Okay, so we're gonna have to see, let's see which one it fails on so we can debug like that one specifically, because we're obviously in a case where it's a little bit more sensitive to exactly what we're asking it to do before we get a problem. So which one are we talking about? Okay, how many of these are there? Wow, so we made it all the way to like basically the end and then we kind of pooped out. So, well, you know, too bad. Let's take a look at cost. So we took 3 steps into number 10, 12, and then we pooped out, right? And so what did we poop out on? Like, what did we do wrong? So let's take a look here. So let's look at terminate results and degrid results and verify terminate, verify degrid. So we're producing the correct terminate value, but instead of picking, and I guess you can see why that's happening is we actually have 2 values that are the same here. And I guess we're differentiating on them differently. So this one picked X and we picked Z. So why did we do that? Would be the first question, right? So what you can see here is if we look at the comparison that we're doing, we basically have two equivalents and one actual. Yeah, so we aren't picking X when we should have been, if that makes sense. And it's specifically this case. Right? So let's go over this one more time. So we know in this case that X is less than or equal to Y. We know that Y is greater than Z. And we know that Z is less than or equal to X. Right? So again, we kind of know this. Oops. So in that case, if Y is greater than Z... Wait. These are so confusing. Let me write that one more time, because that can't be true. X is less than or equal to Y. Y is greater than Z. And Z is less than or equal to... Oops. Z is less than or equal to X. This is just a typing problem at this point. So Z less than or equal to X. Okay, so this is not a bug. This is just a preference problem. We're picking one instead of the other, but it's totally fine, right? So I'm gonna actually call that fine because we don't actually, like in this case, we're just picking a different one. We're picking two out of the equivalent ones, right? And so we could have written this differently to do that. And we wouldn't have had a problem there, right? So that seems fine. Like, I don't care about that. I'm not sure how we continue the validation process with that happening. So that's a little tricky because I'd like to keep it with that validator, but I guess what we could do is say if two of the we could look for exactly that one case and use Z instead. So like we could say in here, something more like maybe like this. So we just say, okay, compute the this values, right? And then we'll use them down here, like so. But I'm going to special case this one kind because we want to match up. So I'm just going to say, look, if this 0 equals this 2, so they're the same, and this 0 is, we'll do 2, is less than this 1, then we're just going to pick it the way we know the other routine will. Right? And again, that's just for me so that I can make my validation work, because if that's the only case that we differ on and it doesn't matter which one you pick, I'd like to make sure we still validate, right? So now I think we've done that complete validation, and now we're using the tables, like our shuffle table and our best table, now are smaller. So I'm just going to go ahead and call these like tbest table, tshuffle table, and tmask table, just so we know what they're doing, because we're about to loft them up into another routine, and I don't really want there to be a lot of confusion about that. Okay. So I'm pretty pleased with that because that doesn't cost us anything at all, and now we don't have to have extra table space or extra lanes involved, so we can literally just reuse the exact same variables that we have in here, and everything should be fine. So now I'm going to go ahead and plop that in the way I was going to do at the start, and then we'll go from there. So here's our t values, and then here's our preamble stuff that we'll work on in a second. For right now, I just want this part. And again, we're only focusing on validation right now. So all I'm going to do is, well, I'm literally going to do this. All I'm going to do is just take a look at whether I can match what comes out of the table, because that's all I want right now. So if we take a look at what we've got here, we just end up with situations where some of these things we already have values for and some of them we don't. So let's take a look. We know that ray_d and inv_ray_d might very well exist because they're the sorts of things we would be doing in this routine anyway. So taking a look, you can see it looks like we have ray_d packed, but not inv_ray_d packed, just from looking at it, right? So ray_d packed here is, so like ray_d4, like that, we have that, it's ray_d packed. But we don't have, say, inv_ray_d4. That doesn't exist. So we can make it pretty easy. It's not a huge deal, right? But it's just like we would want some way of getting this easier, right? Like, I guess I'll just do this for now. And this is not the way we want to do this at all, right? Like, actually, maybe I'll do it this way. So I just want to make a note that all of this stuff is kind of like, there's way too much crap at the beginning. Like a lot of these things are the same and can be simplified and collapsed down. So we'll be able to do much better work here eventually. But for right now, I just want to keep it exactly the same as much as I can, right? Okay, so if we take a look at what else we need to have the @for and the seldim for. So seldim, I don't think we have anywhere. Like that's just something that we effectively just want to copy, right? Because that doesn't actually occur anywhere in here, I don't think. So that's something that we can grab pretty easily. Like we can lemon grab that, no problem. And it's constant, so it's something that doesn't change based on the ray at all, right? It's completely the same no matter what you're doing. So let's grab that somewhere. And where was the seldim from? So I guess that seldim compute walk table. So the seldim just comes from the spatial grid here. So that's just like this, right? So at that point, I'm not sure what we call this. I think this is just ray_d packed, right? So it's inv_ray_d packed, yeah. So it's really just @for, and then we need the step, and well, we just need the step at that point, right? T terminate in this case is wide, as you can see, so I would need to extract that to compare. But that's fine. So in this case, terminate, we actually update that. So basically this value right here that's coming out of the walk table, the problem that we're going to have is we need our own terminate here to track. So just for validation purposes, and then they would collapse. But I want to actually do that work because I, again, really care about validating this because it's just too finicky otherwise. So we're going to have like a tracking terminate here. So I'm going to do something along the lines of like this. And then I'll just slipstream that right on in there. There we go. And here we can also do, well, that's fine. So the terminate verify, in this case, what I'm going to do there is just say, well, whatever the terminate was before, that's what we're going to use. And I guess I can actually just do that here. Okay. So one of the other interesting things about this is since we would now be tracking the position as it goes, I guess like we don't even really need terminate anymore though. Actually. So we probably can just get rid of it. I mean, like if you look, I mean, I guess the reason we want it is, well, I don't even know. I don't even know if we're going to need that. I guess we'll see. Yeah, I mean, so like if you look at what we do, so this is going to be, this will actually optimize this even more because previously when we earlied out, we needed to keep track of terminate for this purpose. We don't even need to keep track of terminate anymore. Because when you leave, we can just make probe p single be the step value that's currently in at x. So basically this, right? That value is just the sample position, right? So we don't, I think, need to worry about that anymore. I could be wrong about that, but it seems like it's fine. So I don't know if we even will need to track terminate. We may be able to just remove it because at 4, which is what we would be doing anyway, will just be what we want. So if we take a look at the starting location here, what we know right now is we're always starting at the center. This will change eventually, but for the moment, it's not going to, right? So let's see where we're at. Yep, I agree. That is a syntax error. Okay. So now we just need our actual step values that we look up in, and what you could sort of see here is that's going to have to get built based on the array anyway when we start. Now, the thing we may want to do is to just, that may want to be in a table, because since we know that the arrays are what the arrays are, we may or may not actually want this, right? So when we look up our dgrid result, I don't know if we actually want to spend the time to make this thing. I mean, maybe we do, maybe we don't. For now, I'm going to do it, but I don't know that I'll want to spend this cost every time we shift raise, because it's sort of a waste of everyone's time. So we may want to try and optimize this step production by just saying, look, we already know what it is. Also, the way it's being done here is not particularly good, so we may actually just be able to fix that part too, right? So who knows? Hard to say. So if we come through here and say we're going to do this computation, and what we're going to do here is the array direction that we're using. Oh, I guess so. This is interesting. So because we sort of finicyize this. I guess we kind of do want to keep these like that, if that makes sense, because we are sort of doing a little bit of an extra dance there, aren't we? Right? Like, we want the absolute value of these things. You know what I'm saying? So we kind of want to say, like, we want the absolute value of each of these, right? Now, what I don't know offhand is, do we really need that? I mean, it flips everything, so I think we don't want that. But we could... I don't know. That one's going to be another thing we should probably look at. Okay. Yeah, so in here, we actually want abs ready packed and abs inv ready packed, right? And in here, this is where we are producing those. So we don't actually care about modifying this. So we can just do this. We can just say, you know, that's the thing. Now, voxel dim is, again, something that I think we just get out of the spatial grid. So voxel dim's getting passed in here. But it's really just this. Right? So now we kind of have an inline validation running of this thing. And what we can do is start to look at it and see if we can get it to behave properly. So we can take a look at a couple things there. First of all, just double check that all this looks right. Yeah. So let's take a look at some of our info here. So in this case, you know, we're just picking two, right? As you would expect. And terminate. Oh, so that's supposed to happen after the fact. Sorry. There we go. Okay. So let's take a look one more time. So here we now have some slightly different stuff we're looking at. So we're looking here at dgrid and dgrid result. Totally wrong. terminate and terminate verify. And in this case, I just want to look at the 0th value. So those two are matching, presumably just because, you know, we haven't gone anywhere yet. It's just the first step through. And so when we are looking at what our deltas would be, that, you know, makes sense. If I look at what we're doing here, I mean, it's pretty clear that you want to step in Z, though. So, like, are we initializing our values wrong, maybe? I mean, we must be, too, because this don't really make much sense. Like, I don't know, maybe it does. Let's see what the radius angle is. No, that does. Fair enough. So I may have played it too fast and loose with this, for all I know. Like, maybe what we were doing there was important in some other way that I didn't think about. Like maybe absolute valuing those things is not what you want to do. But I'm not sure why that would be the case. Right? Because in these, you know that the inverse version is going to be that. Let me just double check that other routine. So let me see what it does. So you can see that all this is doing is just flipping the sign. So it's just guaranteeing that it's always positive, and then it just sets the step to be negative if it was going in the negative direction. So I really don't see why that would cause a problem. Yeah, I don't know. So that all looks fine. I'm not seeing it. So in here we just we don't do any preconditioning to that, do we? We set the starting location, as you would expect, and that's just what gets loaded, right? So there's nothing weird happening there. Yeah, I don't know. I might step through that real quick just to see if I can understand where we're going wrong there. So when we enter, we set up the tables here. The cell dimensions are exactly what you would expect. Let me take a look at what happens when we get in here. So this array goes. This array goes, like 1, 26, -4, 68, which is right. Right? I mean, there's nothing weird about that. So I don't quite get it. That all seemed fine. So that all seems fine too. Let me make sure. I should probably do this shorthand so it's easier to see. So that also seems right. Just failing to see the bug here. So it all looks pretty good so far. Starting at half a cell dim, which is just the middle of the cell, right? Seems reasonable. Again, just does not seem particularly weird. So I don't know. And let's take a look at what the walk table says. So the walk table wanted to take an X step for this ray. Right? I mean, we're X, Y, Z, right? The Z is major, isn't it? I mean, am I just like totally misremembering how we did the voxel? Somehow? I mean, right? So how on earth can that ray, which is definitely taking z steps and only z steps, how on earth could that possibly want to take an x step? Ever. Like, I mean, it's 0. How is it going to move in x? Am I missing something? I mean, yes, is the answer, apparently. What the heck, dude? I mean, this just looks like our walk table stuff is wrong, but how is the walk table stuff wrong? Like, how did that get screwed up? So confused, dude. So confused. Can you please show me something here? So let me run this in here. I just want to see if it's the same thing. What the heck, dude? Like, this just seems like garbage. I'm so confused about what's going on here, right? Because the walk table... Like, what was the starting index for the walk table? For just, let's, tell me that, right? Because I'm so confused right now. So here's our initial grid index. And here's our grid index. So we only went like 1 forward, right? And so I don't actually know how long the walk table is. But I'm curious to know. So let's see. So here's the light sampling walk table. Actually, let's see how long it is. Let's see. So here we are computing the walk table. And let's just see what that value actually is. So, I mean, the walk table is huge, man. So all of those should be right. How are we getting infs written in here? Exactly. Like... Like, did I mess this up somehow? I mean, I don't really see how that happened. So let's do some other things. I want to take a look at when we're assigning these, right? And I want to see like what our terminate values are. Top 10 things you can't do with Visual Studio. Like, this just doesn't... You can't do anything like this in Visual Studio, right? Stepping speed is fine. I don't understand. So what it takes a half a second to step. What would you need more? It's like this. This is what you need it for. So this is just totally... Like, something's super bogus here. Did I accidentally like overwrite part of this table or something? Like, what is going on? Because you can see me writing here, like, infs are not getting written to this table. You know what I'm saying? So like I screwed something up. And I don't actually know like what I screwed up, but something got borked when and you know, I probably should just look at the solution walk table. Let me run it that again to the crash point, well, the validation fail. Let me just take a look at what the walk table is at right now. So if I look at solution, so like if I just want to know which index this was supposedly, right? I'm going to go ahead and say no to that. What on earth? Oh, I've got it backwards. I'm like, what? There we go. So actually, I'm way high here, but what the? So is that the end of the walk table then? So confused. I'm just like truly baffled by what's going on. So it looks like we actually were much higher than that, probably because when we accessed the walk table, I don't really know. All right, so let's take a look. Let's set a breakpoint in here and walk through this from start to finish so I understand what the heck is happening, because I have absolutely no idea. So if I take a look at where this is actually breaking, and we take a look here at loading out of the walk table, whatever the sample directions walk table offset is here. So let me just like grab that and see what it actually says, right? So that says 6912, right? So this is, I mean, unless I'm just totally misinterpreting what we're seeing here. From 69112, we're now saying that somehow the walk table minus the solution right source is like, oh, well that's an actual reasonable number. So how were we getting that other number before? What was happening there? Totally don't understand that. Like that was bizarre, right? So there's one. There's two. So it looks like here's one I know, like that's obviously inbounds, right? And yet there's the terminate inf. I just don't understand. So if I look at the light sampling table here, like it's not inf, right? Did I accidentally increment the walk table twice or something? I just don't understand. So let's see. So supposedly, like this is 6913, right? So I guess if I look there, I should see it, right? Sampling walk table 6913. So it's that, right? And what happens if I look at the previous one? It's 0. So I guess one thing I could do is see where that's written. So I know which index it is. It's 6913. So let's take a look at 6913, I guess. I mean, we can just put a frou-frou in there, right? And just stop on the frou-frou, and then we'll get to see it right inf for some reason. I mean, that's what it should do, right? I could do this in HH light prof if I want to, but so there's my frou-frou, right? And so what we're saying here is terminate is inf, right? So the question is, how did it get to be inf? And if I take a look at, to this, so everything is garbage, right? So inf was fine, but the question is how, you know? How did you get it? How did you get to do that? And remember, this is not the optimized, this is just the regular routine. So what's the array D that let you do that, right? So, okay, so we've got a Z here, and somehow, and I have no idea how, like, did I screw this up somehow? Like, somehow the T this values for that, I mean, how did that ever be the case? I don't understand. I mean, how did you get inf by multiplying by 1? I'm at a loss for someone to tell me how you managed that, right? So I'm assuming what you must have done is in a previous round, somehow you picked infinity as your best guess, right? So you basically, you picked a garbage value here, right? So at one point, maybe because of this, right? Maybe I've got that wrong. Okay, so the best dim equals the dim index that we're on. Yeah, so I just don't quite see it. Let's take a look at if it only happens during these cases. I'm kind of curious to know. I should probably go to HHLightProf because there's no reason for running the game. So we're not even going through these cases. We're going through these cases, right? And because we haven't even hit this. We haven't hit this yet. We're doing this and we haven't even hit this yet. So I really don't know where that's coming from. So I guess what I'll do is I'll say, well, all right, so if frou-frou happened here, I'm going to try going back one so that I can watch this roll through here. Hopefully just slightly before things go pear-shaped, you know what I'm saying? So I can watch them go pear-shaped. So let's see. Here we are. We still have reasonable values. So we can now, I think, hopefully, watch what happens. So here's our T this values for the next step. We've got negative infs here for some reason, which I'm not sure why. I guess because these are negative, but why are those negative? Someone want to tell me why those are negative? So I guess the reason those are negative, so that's kind of weird. So the reason those are negative is because these are negative zeros, but really we wanted to abs this. So really, I think this was just a bug in the original that we just didn't know about, right? Because really what you want here is to say, look, we need to negate this in the case now, but in either case, this just wants to be absolute value. Because those negative zeros are causing us a lot of problems, and I think they were just wrong in this routine. And when we did the absolute value part of things there, I think that would have fixed that, right? So here, we just want to do this. right? So now those two routines are doing the absolute value bit. And I think that's more what we want. So let me just see if that helps us at all, because it seems like we would want that, right? All right. So let's see what happens here to our T this. Okay, now it's doing what I want, right? So like now we shouldn't get into this disaster zone of like getting corrupted by garbage. Yeah. So everyone's fine now. Okay, good. So now let's see what happens in the main routine. Do we get errors there? No. Okay, so that was actually just a bug in our original routine, right? So that was just a screw up. But everything else validated. So now we know that like the stepper is now validating. So I should be able to now yank the original version of the code and see what happens. Like this is now running without any validation problems in the actual lighting, right? That was an interesting one. So when we go through this piece of code now, I should be able to just say, all right, so this piece here, where we do the dgrid values and the cost metric still wants to do the same thing it was doing before. But now I believe this stuff here, I think we can just sort of do an if zero around it, right? So I think we can do this. And I think we can do a terminate equals terminate verify and a grid index plus dgrid result. And I can nerf this. And I think that gives you what you need. Because now that's just using values we know were exactly the same. Like we know terminate verify and terminate were equal. And the dgrid was equal, right? So now we are doing the stepping in the routine proper. It's not the optimal way to do it because we've got a lot of extra cruft in there for no real reason that we should be able to get rid of, right? But I can now, I think, go take a look and just see like how far away we are on speed for having made that change. So now we're not doing table driving. And we can see how fast we are, right? So that's pretty brutal. Like that's like way, way slower. You know what I'm saying? Like way slower. And so the question is it way slower because of something that we can fix? Or is that just like, no, not gonna happen? Because if it's really that much slower, we'd be in a ton of trouble. Like, there's no way we're going to be able to deal with that. So I also would wonder, like, is it, if I do this, and again, I'm just wondering. So it looks like it's literally just the fact that we are doing these computations in here is enough to make it cost too much, right? So yeah, like, I don't know what we do about that. Because we're not really doing very much. You know what I'm saying? And I guess one question, though, is I guess that doesn't really prove that this necessarily, like this part here, is the culprit either. Because when we remove this part, we also remove all of this stuff. Because if no one accesses it, right, then you're not going to have to put that code in there. So I guess I don't really know, like, you know what I'm saying? Like, I don't actually have I don't have a solid feel for like to what extent the setup is expensive. So yeah, one thing I can do is inv-ray-d already is here, so maybe I'll also just do maybe I'll try to do something a little bit more clever here so that these divides aren't there. I don't know. I don't think that's really going to be much, but it could. I mean, it's really hard to say sometimes what that would actually look like. But so one problem that we would have too is that in this case, the inv-ray-d packed, we kind of want to zero out that lane as well, and so that wouldn't actually be good because I don't know what 0 over 0 or 1 over 0 is going to come out to, but it's not going to be 0, right? It's going to be like undefined or something, or nan, and we would probably rather not be nanning around, so that's hard to say, but I don't remember what we did for that in the fast routine. Did we just set that one? Yeah, we did. Right. But yeah, so this is bad, and like I said, I'm not really sure what to do about this. So we have two choices. One, we can back off this avenue of optimization, and wait, that must mean I still have the one, we can back off this avenue of optimization and say, look, that's just not going to cut it. I mean, it would be nice if it did, but it's not going to. The other is we can try to see if we can optimize that stepping to not be so bad, right? And I really don't know, like I said, I really don't know how much that's costing. So another thing that I might want to look at is, like, suppose we actually did one again where we sort of do an if one on this and an if one on this, right? So we keep both of these pieces of code in there with the validator. I'm just curious, to what extent is it just the dependency on that? Oops, that's bad. I guess this doesn't validate right now for some reason. What did I do there that breaks that? Because we just were validating moments ago, right? Is our abs inv-ray-d packed wrong now or something? What did I do? Show me where the problem is. So what happened? Because we were fine, and then I poked it, and we weren't fine, and I would like to know why. So here we are with what the walk table. Well, actually, I guess it's not that anymore. But here's what our. Oh. I mean, that I suppose could do it. Let me see. So is it just that I'm doing this in the wrong order now? So if we look at how this gets initialized, right? Like, so we're taking terminate from the walk table here. Here where we produce terminate verify. I'm wondering if that part is just the part that's busted, right? Terminate verify. So those are both 0. In this case, it loads the one from the walk table, which is whatever it is. Here, you would validate them before adding. And so this part, let me just... There we go. Nope, I'm wrong. So how did I bust that? What did I do wrong there? Like, something's weird. Is this not getting initialized somehow, or what's going on? So these are both starting out at 0. We load from the walk table what the new terminate is here, and we use the dgrid value and all that nonsense, right? Oh. Right. Okay. So we're still validating properly now. So that was just a slight false alarm there. So yeah, so I don't know what to do. I think this is a good place to stop because I'm going to need to think about this or ruminate on this. So like over the course of the week, I'll have thoughts about it. Because I really do need the grid squares to get bigger, but the question is maybe I need to do something else to make that happen, and we still need to be able to load out of tables, right? Because just the speed hit there is just really, really bad. And again, I don't know if something else is, we can inspect it a little bit more carefully later, but it definitely, like, that's just a really, really unacceptably large jump, right? And so I don't actually know what's so horrible about it exactly, but... And you know, I could take a look to it, what the code looks like. This is a little annoying because it looks like this is, since this is multi-threaded, it's a little bit harder to like watch it go through. But what exactly is... So here's the move mask. So that's here, right? And here's the comp PS. So that's here. There's the shuffle. There's the mull. And I don't really know what all this is, though. So, like, I'm assuming some of this stuff got slipstreamed in here. Like, maybe that's like loop counter stuff. So deck, add. Is that just maybe for this? It's weird. Yeah, I don't know. Anyway, there's the move mask. Here's us doing something. I'm not sure why we would be doing this exactly. That's trying to load off the table, I guess. And then we've got the P chef B and the, yeah. There's the mulls. that part, I mean, is not part of the optimized code. So yeah, I don't know. We'll have to look at this a little more carefully. We'll go to a brief Q&A, and then we'll save it for tomorrow. I think the first entry of the T-shuffle and T-mask tables haven't changed to X. Oh, you are probably correct. Thanks for that catch, because we just changed that. That's probably never happening because the validation doesn't fail, but you know, it'll happen someday, or maybe it won't. You know, I set a breakpoint on that one before and it never hit, so that's probably why this didn't cause a validation fail, because like we know that it never actually gets there, right? But yeah, like this, to be consistent, that should look like this. Right, so X, X, both times. All right, so that's what that should have looked like. All right. Could we be going out of the cache and that made it slow? I mean, no. I mean, we added, like, if you look at the size of the tables we added, so the tables we added here are 2 cache lines and like 1 cache line. I mean, we're talking about like 3 cache lines or something, right? So, I mean, there are weird things that could happen where, like, if you got some weird aliasing scenario by just putting a table in and it just, like, creates this weird alias, you know, that could happen. But just the cache is 32K, right? So you can't add, like, you know, 512 bytes and suddenly make the entire thing not work. Like, it doesn't really work that way. You could use a little bit more cache and see a slight degradation, but unless you hit a weird aliasing pattern or something, you know, it's really not realistic, I don't think. But it's not a concern I would have until we eliminated like everything else as concerns, if that makes sense. I think I'm out of tea. Yes, I am. Plus, the other reason not to suspect that is that when you turn off reading the walk table, that means the walk table isn't taking up any cache. And the walk table is way bigger than these tables. So if anything, we probably saved cache space here. But the problem is just too many computations, probably. You know, too many dependent computations. So. But, yeah. We'll take a look at it next week. We'll see what happens. All right, I'm going to wrap it up. Thank you, everybody, for joining me for the episode of Handmade here. It's been a pleasure coding with you, as always. If you would like to follow the series at home, you can always go to handmadehero.org and pre-order the game. It comes with the source code so that you can follow along with it at home. And maybe you can go see what you think about, you know, you can sort of see like, hey, can you figure out why that code got so much slower? Is it just dependency chains? You know, we've looked at a bunch of ways to analyze it. You can load up in vTune. We've got a lot of things we could do. So it's probably the kind of thing that you could have fun with this week if you wanted to sort of learn more about optimization and tracking things down. you should be able to figure it out, right? I'll be back here next week to take a closer look at it. Until then, have fun programming, everyone. And I'll see you on the internet. Take care, everybody.